Okay, so today we're going to cover that worksheet or the study guide. I just wanted to show one thing before we get there. Um, all exam material. Hold on, is it on the right share? There. I'm sure you know this. All the stuff, exam materials in this exam material folder. But I noticed our study guide. The first couple questions were really to the last midterm. So over the years, when you've taught this class, they move spring break around and holidays move around a little bit and the pace of the class. At Manoa, there was a time when they tried to push and do all or do 11 instead of just 10 chapters. Anyway, so today we're going to do study guide 3, which has always been up here, but we got to chapters 9. I think we started a little bit at 10. And so I added in a different uh, it's labeled practice exam, but study guide, same thing, right? But it's 3, and I don't even know how old this document is, but it's got material from chapter 9 and some from 10. So it's the combo of the two, I think, is a little bit better. So this, will definitely be new to people because I just put it up. But we'll cover it, and as usual, there's the blank, and then there's the one with the answers. But since that has more of 9, let's do the normal one that you were expecting down here first. So let me stop this one. Okay, there. So the wavelength for light and stuff was on the last exam. I'm not putting a quantum number like this on there, naming them and stuff. That seems a little bit excessive. I used to do that at Manoa because there's a couple of chemistry on the faculty there that are somewhere in between physics and chemistry. They really love the stuff. So, but it doesn't seem as relevant for us. Okay, so let's skip down to 7. This is a pretty straightforward one. Give the number of core electrons for cadmium. So this just goes to looking up where cadmium is. Just have to stop the share to go back and forth, but it's not that big a deal. Let me open up. Periodic table. Okay, so you come and you find cadmium, it's the 48th element, and the core electrons are the noble gas above it, right? So cadmium here is in our 5th period, so you go up to the 4th period, and it's the noble gas that's over there. That one is krypton. 36 is the number of protons. Now I kind of forget what it even asked us, so let's go back. And it just wanted the number of electrons, which equals the number of protons, so 36. 8, this one's pretty easy. Some of these are a little, I think this exam will be easier because it's things like this that you can either rationalize, dig through your notes. It doesn't take as many calculations and whatnot. So I think this test will be a little bit easier or quicker. Protons, neutrons are in the nucleus, right? And the electrons they're coming and going and moving in those orbitals. So if something has a +2 charge, it means it lost 2 electrons. That's a really easy one. All right, are the following paramagnetic or diamagnetic? All that means is there an unpaired electron? So, I mean, this is not quite fair, like test type question to have this many on there, but I put something somewhat similar. But there's a lot of examples in here, and it's it's because it's an exercise to go and get the various electron configurations. So this first one, titanium 3+, you take 3 electrons away, and you'd be left with 1 electron. So anytime you have an odd number, it's always going to be paramagnetic. Manganese is 4s2, 3d5, so you're going to have lots of unpaired electrons there. Calcium and calcium metal are right next to each other. They're in group 2 and a 2+, so they're diamagnetic either way. Chromium, you go and find chromium on the periodic table. It's 6 elements over from group 1, so all 6 electrons are gone. So it basically has the same. It has the same electron count as the one before it, calcium 2+, that argon, the noble gas before. Sodium, again, a group 1, that electron's gone. It's just the noble gas before it. Nitrogen with a 3-. So it's normally 3s2, 3p3, but if it's a -3, you add 3 electrons in, and that gets you to p6. Again, another noble gas, and those are all paired up and diamagnetic. Chlorine, just the atom, is in group 7. So it's always going to end, everything in that group 7 ends with s2, p5, just depends on the row. And it's missing 1 electron, so there's going to be 1 unpaired electron in one of those p orbitals. And this one wasn't asking, doesn't care about which orbitals they're in or anything. S2-, sulfur is right below oxygen. It's in group 6. This is the cross-coupling stuff of charges we did earlier, right? Group 7 was -1. Group 6 was usually -2. That gets you to the noble gas configuration. P6 is all filled, so diamagnetic, and you can show that shorthanded with just the argon. 10 is light, which we had on the last test. So we can actually skip those. 10, 11, and 12. 13, choose the orbital diagram that represents the ground state of nitrogen. But I guess I'll stop to share this though. Right, so you come to nitrogen in the periodic table, right? Groups 1 and 2 is the S block. From boron over to the noble gases is the P block. So we've got 2 S electrons and then 1, 2, 3 P electrons. So fill up helium, obviously, that would be filled. So you can see here, it's the ones above, right? So C doesn't make any sense. It's got unpaired electrons and 1s and 2s. That doesn't make any sense. As we get to D down here, it's missing P electrons entirely, so that doesn't make any sense. So we've eliminated those 2, right? Then A and B, the 1s and the 2s are filled. That looks good. Okay, what's the difference here? The 2p has 2 electrons and 1, and then 1 unpaired versus 3 unpaired. Which one of these is correct? This is sort of a roundabout way of asking you the Pauli exclusion principle, which you don't need to know the reason, have it memorized why, but it dumped and then restarted and then muted me. So I don't know why it does that. Okay, back to the one where we're at. I'm not sure when it cut out exactly, so we'll rehash a little bit. Nitrogen, we know we needed the 1s and the 2s filled, so that's why how we eliminated answer C. Right? D had no p electrons, so that got us down to just A and B. And then the critical thing here is that electrons are negatively charged and they repel each other. So they won't pair up like this, especially the way this is drawn with a straight line implies energetically that each of the p orbitals is equal in energy. So there's no reason to have them paired when there's another empty equal. That equal energy is called degenerate, a degenerate orbital available. 14, which has the smallest atomic radius. What this is meant, and I think I put one of these on here, whereas we have two trends, and the two trends were as you go down in the table, like planets around the sun, the radiuses get larger. And then there's a contracting effect as you go across to the right. So you can zigzag your way from each one and rationalize why each one is bigger. And this is cesium to fluorine. So cesium's here, and in this, it was all sort of over and then up. Keep working your way. I forget the exact elements in between. But it got to fluorine of all the choices. And so you could rationalize why everything further to the right and above from each element, and it would just be a zigzag till you got up here to fluorine. So of the choices, fluorine is the furthest to the right and the highest in the table. Obviously, neon and helium are both further to the right and above fluorine, but that wasn't an option in the multiple choice options on it. What's the electron configuration for scandium 2+ ion? So, well, the answer is already down here. If we go to, should just put a periodic table on this answer key. I made this answer key, before COVID and Zoom switching. But here's scandium, 4s2, 3d1. From the pictures that we saw, the D is higher in energy. I wouldn't really split hairs between if you put, so if we stop it, you could see that depends on, you have to know which one of these are higher than, and a little bit higher Chem theory. I won't put one of these ambiguous ones on. So you could put 3d1 or 4s1. Back. Right. Either way, there's only one electron, and that's a critical thing for this. Which orbital it's actually in, S versus D, is really only important for higher chemistry classes. So I won't put one that's slightly ambiguous like this, but the rest have been fine. 16, orbital diagram for an oxygen atom. So, you go get oxygen off the periodic table, it's the 8th element. So 8 protons means 8 electrons for just an atom. The picture got dragged down here. So basically it's the same as the one above, right? 6 valence electrons. You would, like with nitrogen, you would have one in each of the orbitals. So you'd have half paired orbitals, and then that 4th electron, it doesn't matter which one it goes in conventionally wise. People put it in the first one just because that's how we write in English, but it doesn't really matter which box you put it in. Since they're grouped together like this, that implies they're degenerate, that their energy is equal. So it doesn't really matter which orbital you select. 17, which species would you predict to have the largest radius? So looks like our choices here are oxygen, sulfur, and then an ion of oxygen and an ion of selenium. So as you go down in the periodic table, the radius gets bigger. So you would obviously think if you're looking between A and B, sulfur's below oxygen, so sulfur's going to be bigger than just an oxygen atom. Then between, it might be hard to guess maybe between oxygen that's 2+ and sulfur, but when you remove electrons, it should contract. So you would argue that oxygen, that C, oxygen 2+, should be the smallest, and then oxygen, and then sulfur. Then when we get to selenium plus, selenium is directly below sulfur. So that trend tells us that the selenium would be bigger, but the positive charge has a contracting effect. So whether B and D, which one is bigger than the other, it's hard to say for sure. But when you add an electron, the radius swelled a bit. And so the selenium, the minus charge should make it the biggest. And then the selenium with a -1 should be bigger than just selenium on its own. And that selenium on its own would be bigger than just sulfur. So it's the furthest down and has negative charge. So it has both of the two trends of adding and taking away electrons and location in the table. 18, which is the correct shorthand electron configuration for GE? Let's switch the. So germanium is these red elements. These are your transition metal metalloids. I mean, this periodic table calls them semi-metals. Some of them call them metalloids. Anyway, the point is these are the ones, and a few of indium and tin. These are the things that go into making a lot of electronics because they have good features like conducting electricity and other metallic properties. But they also don't have the full metal properties like lead that is really dense and heavy and large mass, or mercury is actually a liquid. And you don't want them to have the properties of, say, copper or a carbon up above. You need some metallic nature to it. And if you're into and have used, anything engineering-wise, and by that I mean even like skateboards and bicycles when you're a kid, they use a lot aluminum for a lot of things because it's pretty strong, but it's very light. And it's also not reactive like other light things like lithium. We use those for batteries. Okay, anyway, so back to our point here is germanium. It's the 32nd element. We're in the 4th row. That means argon is going to be our noble gas. We should have 2 electrons for the 4s orbital. The 3d will be filled, and then 2 electrons in the 4p. So A has the wrong noble gas. Right, B has the right noble gas. It's got the 4s, the 3d10, but it's got too many electrons, too many p electrons. D looks like right noble gas, right number of electrons, but for some reason there's 2 electrons missing in the D and there's 2 extra. So it's the same correct total number of electrons, but 2 are in the wrong spot. So C is the right one. Ionization 19, ionization energy is the energy required to remove an electron from a gaseous atom. That's generically like this, where you've got some element and then the plus, right? Because it's lost the electron and the electron comes off. The first ionization is the first ionization larger than the second ionization. So this has to do with whether you're removing that electron. It kind of depends on the atom. This is kind of, I'm kind of surprised. I call this really a goof and left it in here. But it is like the main point arguing is that the second ionization, you have to remove something from something that is now positive. That's really what it's getting at. I guess it's fair in that sense, but generically, when you think of things all over the periodic table. All right, so in just general trends, what it's getting at is that the next process would be where the X plus is now the reactant, and it's harder to remove an electron because it's negatively charged away from something that is now positive. Yeah, I guess it makes sense. It makes sense when you think about it in a grand sweeping generalization and not atom by atom, case by case, which is sort of like, you know, this problem 9 above, and then it looks like the next one too. I got a little distracted by the next one. 20, rank the following elements by their atomic radius from smallest to largest. Again, this is going to be where you can compare one to the next. I don't have these memorized, but helium, neon, carbon, germanium, chromium, tungsten, barium, frankly. Okay, I can kind of follow these. So whenever I put one of these on the table, it has to follow the general trends that we talked about. And last time I just asked you which one was the smallest. This one's saying ranking it. And so I think it was, right, we went to helium, then to neon, then maybe it was carbon. I forget exactly what elements, but notice the trend right down over somewhere we probably went down like aluminum, and maybe down to, yeah, carbon, then we went down to germanium, and then it was some nickel or something. I remember we got to yttrium or something, and then anyway, it ended at Frank. So there won't be any where I'm asking you to go against general trends. And so those two problems are they're very similar, right? The one where fluorine was the answer. That one you were working up and over and just getting to the smallest. This one, it was down and to the left until you got to the largest. All right, and that was actually, or obviously kind of quick because some of those were really from our last exam. Okay, so notice here, right, there's nothing up here with equations in this one, and it's because most of the stuff you're doing is trends or just counting a few electrons or a place on the periodic table. I don't think you'll even really need a calculator for this exam, which is a lot like organic chemistry. It's mostly manipulating and drawing the molecules and talking about reactivity in OChem. So you definitely don't need a calculator in OChem. Okay, this first one, draw the best Lewis structure for the free radical NO2. What's the formal charge on the nitrogen? So formal charge is valence electrons minus the non-bonding minus half of the bonding electrons. So nitrogen is going to be the central element. If you connect those two by a single bond, and then you start putting in all your electrons, then you get to a situation like this. And we already knew it was a free radical, right? Because it told us free radical again means that there's one extra electron. So you could really do resonance structures. Right? You could take the 2 electrons here on this one and push it in and make a double bond, but then this electron has to come off the nitrogen, right? Because right now the nitrogen has 7 electrons around it. And it's predominantly going to stay there. That's the best structure. And so valence electrons, this is the best one. Valence electrons, nitrogen has 4. Non-bonding electrons is that one blue lone pair. And then minus 1/2 the bonding electrons. So there's 2, and then the double bond 4. So 6 divided by 2 is 3. So 5 minus 1 minus 1 gives us +1. And whenever you get a free radical is always going to be a +1 or a -1. A lot of times it's a -1. This is a little bit rarer of an example. 2, which of the following processes are endothermic? So this has just some of the different things we talked about. Here you can think about this first one. It's like two magnets coming together. So that's obviously going to be exothermic. That's going to be favorable. The next one, we've got two bromine atoms going to make bromine gas. So that's basically what we did with electron configurations, and then the s and p orbitals and making bonds. So this is unfavorable, right, to have just two radicals. Bromine has 7 electrons, so you have these two radicals out there, and it's more favorable for them to come together and make a bond. You never see two bromine atoms floating around near one another. They form together and stay together as Br2. Calcium, solid to gas. This is, right, if you were, what dry ice does, if you've seen that around Halloween. Or, if it wasn't a solid, say liquid to gas, that's when you boil water on the stove, that type of thing. Anyway, you slice it, that's energy going in. So we've eliminated it asks which are endothermic. So we eliminated the first two, and then this one is the most common one that right? You've done that before on the stove. So that one's kind of the easiest. D, we've got sodium metal and half of an oxygen atom coming together. And this one looks like all the stuff we did a couple chapters back, where you've got some element. Planes, trains, and automobiles, or basically it's carbon and hydrogen, but you react them with oxygen and you make the oxide compounds. This one happens to be sodium instead of carbon and hydrogen, but it's still a combustion reaction, and these are always exothermic. 3, identify the compound with covalent bonding. So A is ionic, right? A metal and a non-metal. B is just a metal. D, helium, is a non-metal, but it's a monatomic gas, helium. So there's no bond. E, you could actually argue, because it's just saying sulfur, which is a little misleading, I'd say, a touch. I'm just pulling up on Wikipedia here, and I'll share the screen. Yeah. So there are forms of sulfur, right? This one is, I guess, 16 atoms. I'm sure there's several different kinds. It gives a little information about its different properties and whatnot. Maybe put in atomic structure. No, that's going to give us the individual, maybe allotropes of sulfur here. Few images of allotropes. And there's a sulfur bond there. So this one is not one that I would put on the test. I'd say all the rest of those are fair, but but it's, on an exam like this, like if I did something like this, I would go back and I would let either C or E be correct. But I'm pretty sure I don't have something like that. From our class, you would just assume the same thing. It's a single atom, but sulfur doesn't exist as a single atom. It exists in all those different allotropes, those different forms and stuff. But pretty sure I don't have ambiguous ones on the exam. But the rest were easy to either eliminate, and then water is our classic example that we talked about, and you'll use and talk about in all your science classes. The trend in ionization energies. So ionization energy is removing an electron. And it gets harder as you go up because the electron that you're removing is closer to the nucleus. And then just the same with our radius, that contracting effect. 5, which of the following ionic compounds would be expected to have the highest lattice energy? So this is basically just indirectly asking you about the radius. It looks like A through D, the metal is all lithium. So that's really not the issue at hand. And then it's group 7 only, fluorine, chlorine, bromine, iodine. You look on the periodic table, fluorine is the smallest, iodine is the biggest. And since when the radius is smaller, then those charges get closer to one another. And again, think of them like little magnets. So the closer two magnets get to one another, the stronger the interaction. And this is why, it's like magnets on your fridge. The larger the piece of paper, the more difficulty the magnets on the fridge have holding it to the fridge, or you need several magnets. So the thicker the piece of paper, the harder it is. Like refrigerator magnets probably can't hold like a piece of cardboard to the fridge, but they can hold a piece of paper, and the difference is the thickness, which is equivalent to the radius. 6 looks like this one is electronegativity. Only 3 elements, so pretty easy. Fluorine, sulfur, and selenium. And so fluorine is the most electronegative. Sulfur is 1 over and down, so both trends following the trend. So sulfur would be less than fluorine, and then selenium is directly below. So just one trend there, but follows the trend. That's a really fair type test question where there's no exceptions or against the trend. And that one was a bit easier since there was only 3 elements. There weren't 7 or 8 or something. 7, there's a compound, ClF. It contains blank, and this picture wasn't there. So this is the kind of thing, good example for our tests and for OChem people where you'll have to go draw it yourself. In OChem, they'll evaluate, the drawing. In here, we're obviously not doing that. It's the exam's on Mount Lima, but chlorine and fluorine both have 7 electrons, so they share each other's 7th, so they both feel like they have 8. There's no metal, so it's not ionic. They're not the same element, so it's clearly not non-polar, which only leaves really one option: polar, covalent. Then between C and D, it's just where are the charges. So this one kind of asks everything. Do you know covalent bonding? Do you know Lewis structure? Do you remember electronegativity and that there's polarity to the bonds? So kind of a question that's sort of easy, but hits a lot of topics. 8, how many of the following elements can form compounds with an expanded octet? The only thing that can have an expanded octet is an element that's in the 3rd row. So phosphorus, krypton, xenon, and boron are our options. Boron's here in the 2nd row, so it's obviously not it. There's phosphorus. Now we're in the 3rd. That's fine. And then here was krypton and something else. But boron, I remember, in there was the only one that's in the 2nd. So it's really just the 2nd row that has to strictly adhere to the octet rule. Oh, xenon, krypton, and xenon. Those are both noble gases, even further down than phosphorus. 9, another paramagnetic example. Or is it the same problem? Ah, it's the same problem. So I must have copied this one over, flip-flopped it. Again, these two are study guides are from different semesters when they moved spring break around and holidays. And sometimes the holidays, like for our class, Monday, Wednesday, uh, several holidays set you back, and then wherever they set the spring break week. Anyway, number 10. Choose the compound below that contains at least one polar covalent bond, but is non-polar. So for these, you'd have to go and draw them all. Just by glancing at them, it's pretty easy to tell what the central atom is, right? Water is bent, oxygen's the central atom. The bonds, both bonds are polar, but the overall molecule is polar in that one due to the bent structure. The sulfur, the same thing. D here, CH2F2 looks just like what you see over here, except with fluorine and not chlorine. So the two chlorines are, the bonds make those polar, but there's no way for it to cancel. This isn't showing the three-dimensional tetrahedral structure of it. And SF2 basically looks just like water, right? So oxygen and sulfur are both in the same place in the periodic table. Hydrogen and fluorine both want to form one bond. For hydrogen, 2-electron rule. For fluorine, 7-electron. But they're basically going to have the same structure. I'm just pulling it up on Wikipedia. So very similar. Looks like this where you might think it's non-polar, but the correct way to draw it is like this with those two lone pairs. Pushing it just like water gets pushed and making it bent. And up here it's saying, someone out there measured it around 98 degrees. And carbon dioxide is sort of the classic one that you introduce where the bonds are polar, but it's linear and symmetric. And so those vector addition, they cancel each other. I think there's a couple like this. Choose the best Lewis structure for CH2Cl2. All right, so if you just pick the central atom, carbon is the least electronegative, so you would think it's going to be the central atom. But let's eliminate things like this one. This hydrogen here has 2 bonds, so that's 4 electrons. So that one's ridiculous. E here, this carbon in the middle has 4 4s, 8, 10, 12 electrons around it. That doesn't make any sense. So we've eliminated several of these. What else? This here, A, the carbon is in the middle, but the chlorines are out there. The hydrogens do have 1 bond. What's the problem with this one is the carbon has lone pairs on it. Carbon never has lone pairs on it. So A doesn't make any sense. E doesn't make any sense. C doesn't make any sense. So we're down to B and D. And what's the difference between these? It looks like just the lone pairs. And so that's the correct one. And they've drawn it like this, but really you could draw it like that. And remember, it's got the tetrahedral structure. Carbon has a tetrahedral framework. When you get to OChem, they don't require you to draw the lone pairs anymore. They're going to assume that you know them. So in in OChem, this answer would be fine. But when we're learning it here and the lone pairs are important, they want you to draw them out in the book. 12. Give the number of valence electrons for ICl5. So this might seem kind of tricky at first, but it's really just you go to what group, the location of the elements. Iodine's in group 7, so is chlorine. So really it's just 6 elements that are in group 7. Group 7 is a combination of the S and the P electrons. So 2 from the S and 5 from the P, so 7. So 7 times 6 is 42. 13, which of the following contains an atom that does not obey the octet rule? A is inner ionic metal and a non-metal, so it doesn't apply. B, we're getting closer, but tin is metal, so it doesn't apply. Then D, we saw this one, I think, earlier, but the chlorine is in the third row, so there is the potential for the expanded octet, but they both have 7 electrons, so they're just going to form one bond. We saw that one earlier, so that one seems fine as well. Then it must be C, right? It's got 5 fluorines. Fluorine only makes 1 bond, so they have to all be bonded to the chlorine. And that would mean, at the very least, that chlorine has 5 bonds times 2 electrons, 10 electrons around it. That's obviously more than 8. So the only answer that makes any sense is C. 14, this is that same question from the last one, where you worked your way through by the trends up and over until you got to fluorine. Oh, scandium 2, looks like a lot of these overlap. We did all these. So it's like the second half, sort of half and half. It looks like this one probably has, this is the one I should have posted anyway. It's better. It has 8 and 9 and a little bit of 10. Okay, that was obviously a little quicker than I thought since some of those overlapped. The problems are a bit easier, I think. Let me, but we could do some worksheet ones. There's no reason to end class. So I'm going to pull those up, but if you have any questions, comments, want me to recover anything that was on here, just let me know in the chat box. So it looks like 10 kind of went to the last exam. Let me open up 11. Eleven's really short and 11 too easy, so oh. Yeah, we'll do 12 and a few others. At least they're on the right chapters and stuff. All right, let me open up. Okay, here's 12. Which of the following is true? Covalent bond is formed through the transfer of electrons from one to another. No, that's describing ionic. A pair of electrons involved in a covalent bond is sometimes referred to as a lone pair. A pair of electrons in a covalent bond is sometimes referred to as a lone pair. It's kind of vague, so it's just not the best answer, right? There are obviously lone pairs there, but a pair of electrons is also a bond. So, but it says sometimes. This must be one of the problems she put in here. I haven't looked at these in years, but that one would be one I would cut out. I wouldn't have on the test. Is it possible for is it possible for two atoms to share more than two electrons? It is not possible. I'm so sorry. It is not possible for two electrons to share more than two electrons. That's false, right? As you can like it. So it's worded fine. It is not possible for two atoms to share more than two electrons. So if they're sharing two, that's a single bond, right? If there's more, then the radical like example that we saw could be in there, or double, triple bonds. Single bonds are shorter than double bonds. That's definitely not true. In a covalent compound, the shared electrons interact with the nuclei of both of the non-bonding atoms, thus lowering their potential energy. So this problem, except for that one kind of strangely worded thing, is basically describing ionic bonding and covalent bonding, and then try to think of other things that that were false. 2, which of the following represents Lewis structure of chlorine? These ones like this will seem pretty easy if you're doing the Lewis structure for actual compounds and the shapes that we got into. Right, so it's just 7 electrons put around a chlorine atom. Which of the following represents Lewis structure for calcium 2+? I mean, right, this is pretty easy. The electrons, they shouldn't be there. The Lewis structure never shows core electrons, so it's just a 2+. Give the complete electronic configuration of Br-. So Br is bromine, it's in group 7. And then the minus signs means adding an electron to it. And so you're filling that octet. So one element over and fill up that P, so it'll end with 4p6. And then whatever the noble gas is next, I think that's xenon, but I forget if it's krypton or xenon. Use Lewis theory to determine the chemical formula for the compound between aluminum and oxygen. So this is meant to tie together what we already did earlier when you did naming and charges and places, locations on the periodic table. Right, oxygen's in group 6, and so it wants 2 electrons. Aluminum's in group 3, so it's willing to give up 3. 2 and 3 aren't obviously aren't the same number. So if you have 2 aluminums and you have 3 oxygens, then you can move 6 electrons back and forth. 6. Place the following in order, decreasing magnitude. So lattice energy. So again, this is just on radius size. So which 2 are the smallest? It looks like the metals have gone down. Sodium's at the top, then potassium, then rubidium, and then even its counterpart, the same trend. Fluorine is above chlorine, and chlorine's above bromine. So sodium fluoride should have the highest interaction, favorable interaction coming together, then the calcium, potassium, calcium, then the rubidium, bromide. Seven, I didn't put one of these on here on the test. It feels a little Chem engineering overdue to me, but plus we already did, Bornhaber is just these 2 that came up with this treatment, and we already did Hess's law, so it's not like you haven't had been introduced to and learned the experience of adding sequential chemical processes together. And so this is just going through and adding these up. with little caveats like, here, for example, the oxygen atom plus the electron, if you have, oh, it's just doing calcium. This is from a problem where they had calcium oxide at one point. So anyway. 8, identify the weakest bond. Pretty simple. From what we covered, I pointed out that a double bond isn't actually exactly 2 times a single, and a triple isn't 3 times a single. We didn't get to the part in chapter 10 why that is, and that has to do with the S and P orbitals. But for now, you should know it's just purely the number of electrons between 2 atoms. So if there was a radical that could go in between 2 atoms, that would be like 3 electrons, and that's what resonance structures are basically, right? If they're shifting single bond, double bond, it's really more like 1.5 bonds because the electrons are moving so fast in that resonance structure. But this one's simply saying, single, double, triple, the strength increases. And we'll look at how you make a double and triple, and that it's a bit different than the simple way it's been presented here. Let's see, 9. Using periodic trends, place the following bonds in order of increasing ionic character. Looks like they held the metal of the ionic 2 of your choice constant, right? It's silicone. So you're not really then looking at the silicone. You're looking at the other element that's there. These are all in the same period of the periodic table from phosphorus over. So right here's phosphorus, and it was silicone, right? These, so the SiP, the SiS, the SiCl bond is basically what you're comparing. Well, the silicone is a metalloid, so it and anything further to the left is obviously has more metallic character. Thus, you have less metallic character as you go to the right. And in fact, right, phosphorus and on this periodic table, you can see phosphorus and sulfur are solids, but then the chlorine is actually a gas. So obviously gases at room temperature pressure are never metals. So, but that's basically the implication, is that you're going over this metalloid staircase. So the elements as you move to the right get less metallic. Choose the best structure for OCl2. It looks like you didn't choose it actually, so wanted you to draw it, or maybe the options were there, but this looks just like water or the SF2 that we saw, right? It's a group 6 element, this time oxygen, so 6 electrons, and then it is a element that only wants to form 1 bond. In this case, it's chlorine, but it would look basically the same if it was fluorine or hydrogen, so very similar to water. Again, the way they have it drawn here, keep in mind that tetrahedral 3-dimensional structure, it's bent, it's not linear. That was 12. 13. I think it's that one is the same picture on the same problem from the study guide. So let's do 2. This is one that I wouldn't put on a test, but these worksheets are meant to make you go search and think and whatnot. And the reason for that is Be is beryllium. It's a peculiar, strange element so high up in the periodic table that it doesn't need all the electrons like an octet. So it has 2 valence electrons on its own. Then the fluorine has 7. The fluorine wants to make 1 bond. Beryllium's the lower electronegativity, so it would be your central atom. You make 1 bond and then you draw the lone pairs in. So D is where you would start. And then the other answer is like E or A are where you start putting those lone pairs in and making multiple bonds. So that you could get 8 electrons around beryllium. But beryllium is this weirdo element that doesn't need 8 electrons around it. So I won't be putting this example in the test, but keep in mind this worksheet's meant to, they're designed for students to do them in small packs and pairs and go search for the answers and discuss and draw and even come up with 2 different ones and then look up which one's more accurate. 3. So we did a pretty similar one, right? The central atom has to be, it's pretty obvious when it's like a subscript that has multiple elements around it. Whenever it's, A, B, 5, then A is the central atom and there's 5 B's around it. So chlorine, I guess, could be the central atom, but it's less electronegative, so it's more likely not. So this is the more likely structure. Anyway, there's 6 elements total. They're all in group 7. 6 times 7 is 42. So you make the 5 individual iodine chlorine bonds, then the rest of the electrons you put in around as lone pairs, and then if you need it, which you do in this case, the iodine gets the last 2. Given the number of valence electrons for SO4 2 minus, carbon sulfur has 6 and oxygen 6 as well, and you've got 5 of them. So 5 times 6 is 30, and then the -2 charge means just add 2 electrons, so 32. 5. Draw the Lewis structure for NO2 minus, including any valid resonance structures. Describe the resonance hybrid of the nitrite ion. Looks like I didn't have the structure in here. Let me just find one. This is doing radical. Where's a better or the best one? There, that's better than what I got. So nitrogen's in the middle, right? You make the single bonds, you start putting in the lone pairs. And then we have this option here now where you can flip-flop where on the oxygen is where the single and the double bond is, right? And nitrogen's happy this way, oxygen's happy. One of the fluorines is negative, but overall that's what the charge was, so that's what we needed, so that makes sense. If we look back, nitrite ion contains 1 NO single bond and 1 NO double bond. Well, sure, but right, it mentioned resonance structures, so I don't know if I'd circle that right away. I mean, obviously you can see the right answer. The nitrate ion contains 2 NO double bonds now. The nitrate ion contains 2 NO single bonds now. So it's definitely not C or D. Then if we look at B, the nitrate ion contains 2 NO bonds that are equivalent to 1.5 bonds. That sounds the most accurate, right? Again, keeping in mind that it mentioned resonance, which means, and then it said hybrid, right? So that's really telling you that the molecule is a blend of the 2 different structures. 6, draw the Lewis structure for carbonate. Any valid resonance structures, which of the following statements is true? So this one looks kind of like the same thing. Pull it up. Right, so there's carbonate structure. Oh, this one looks like it's got animation here. And works through solving it. Let's click on that one. Yeah, this is a good, kind of a better one. And oh, and it's got a YouTube link. Okay, the carbonate ion contains one CO single bond and two CO double bonds. That's not true. The carbonate contains one CO single bond and one CO double bond. Yeah. The CO2, the carbonate, contains three CO double bonds. No. The carbonate ion contains two single bonds and one triple bond. No. So this one, we didn't need the resonance like the one above. It was just testing us on drawing one resonance form. 7, which of the following structures, resonance structures for OCN, will contribute most to the correct structure of OCN minus? So again, let's pull that one up. So you would imagine carbon's the least electronegative. It's going to be the central atom. We're obviously going to run into a problem because carbon wants to form 4 bonds, nitrogen wants to form 3, and oxygen wants to form 2. So carbon can't form 5 bonds. So you've got to have, you're going to run into some kind of issue, and that's the formal charge on the oxygen, where it only has 1 bond and 3 lone pairs, and it gets a minus charge. But then it's supposed to have a minus charge, so that seems reasonable. All right, so then it asked us which one, OCN with 2 lone pairs on the oxygen and 2 lone pairs on the nitrogen. That would mean nitrogen doesn't have, nitrogen wouldn't have a 3rd bond and an extra lone pair. So that is the same structure that's possible, right? That's, they're trying to show it here with the equal, double bonds. But that doesn't seem quite as happy like we saw it, right? Then a triple bond between oxygen and carbon with 1 single bond between carbon and nitrogen, that doesn't make any sense. Nitrogen never has 3 lone pairs on it. It rarely has 2 lone pairs on it anyway. All right, then oxygen, carbon, nitrogen, like that, with 1 lone pair on oxygen and 2 lone pairs on carbon and 1 lone pair on the nitrogen. Well, if there's 2 double bonds on carbon, you can't have any more electrons on carbon, so that doesn't really work either. Then the one that we saw, right, 3 lone pairs on the oxygen, which we've seen quite a bit in the examples we've done, and then 1 lone and a lone pair on the nitrogen. So that one is definitely the best, because you've got carbon and nitrogen in their common bonding, and then only the oxygen, which we've seen quite a bit as a -1, and the charge needs to be -1 overall. The other thing, the problem with A up above is there would be a minus on the nitrogen in that situation, and if you're going to have a negative charge, you want it to be on the more electronegative atom, and oxygen is the more electronegative atom. 8, define bond energy. Energy required to form 1 mole bond in the solid phase, energy required to form 1 mole of a bond in the gas phase, energy required to break 1 mole of the bond in the liquid phase, energy required to break 1 mole of the bond in the gas phase. I wouldn't put this on the test because this is just tedious, silly, pure definition of stuff when we covered bond energy. That's a little too easy. You would just look that up, I guess, dig through your notes or something. Our test is a bit more of the Lewis structure stuff. Which compound has the shortest carbon-carbon bond length? So from what we have covered already so far, this is basically the same question above, just making you draw them out. So we've got 3 options here. They all have 2 carbons in them, and then hydrogens. The hydrogens only form 1 bond, so they're the capping or end terminal positions on the molecule, and that's it. And so what this inherently tells us is that A is a single bond, B must be a double bond, and C is a triple bond. So the shortest and strongest bond then is C, and this is that acetylene that's used in welding. Ozone is O3, right? Oxygen has 6 electrons times 3, so you've got 18 total. They're all the same elements, so just one of them has to be in the middle. And so 1 oxygen is +1 formal charge. It's got 1 extra bond and 1 less lone pair, and then 1 oxygen is always going to have 1 less bond and 1 more lone pair than it wants, and it flip-flops back and forth between these 2. So another example of where it's really not a single and a double bond, but 2 1.5 bonds. 11, ionic means a metal and a non-metal. So all of these are either non-metals, and then B is a metal just on its own. So A is the only one that's a metal and a non-metal. That was pretty easy. Identify the substance that conducts electricity. I didn't put one of these on the test. Yeah, it's just, this is just where the term electrolyte comes from. And you'll see this again in Chem 162 when we talk about batteries and electrochemistry, but and there was a picture of it in the book and where the term electrolyte came from. Yeah, but I wouldn't put that on the test. I think that's exactly fair. Use Lewis theory to determine the chemical formula for the compound between lithium and sulfur. Sort of the same thing as above, and when we covered the naming of these things way back when, right, lithium's in group 1, so +1, sulfur's in group 6, so -2, so you need 2 sulfurs for every 2 lithiums, for every sulfur. Identify the number of bonding pairs and lone pairs of electrons in O2. As well as right, so oxygen has 6 electrons, wants to form 2 bonds, bring them together. So 12 total. The happiest way to do this is to make it a double bond in between. So that gets you your 2 bonds, that's 4 electrons. Or from the 12 gives you 8, and then if you have 1, 2, 3, 4 sets of lone pairs, that's all your electrons. And so this is the happiest form of oxygen. Let's go back. What did it ask? 2 bonding pairs and 4 lone pairs, right? All the rest have some problem or issue. Okay. Only a few minutes left, so not really enough time to finish the next worksheet. So I'm gonna stop there, and I'll see you Wednesday. Same as usual. We'll start the classes at 12:30, but the test will open up at 12:35. I'll be here before if you want to ask any last minute questions. I'll email you out the PDF of it, and then the test is an hour long, and whenever you're done, class is over for the day. So questions, comments, thoughts, feelings.
This test, the exam, it's gonna have, you're gonna attach like the test at the bottom, same as last time, right? Or if you scroll down, we can see the test, like as if we wanted to print it.
Yeah, I'll email it to you too, and I'll put it on the Lao memo with the test. When you're there, it should be somewhere, but I guess it's down at the bottom. I don't, since I don't take it as a student, I don't know where the button is, but it'll be there, and then I'll email it out. And if you lose it or can't open it or something, just let me know in the text box, and I'll email it to you directly.
Okay, thank you.
Yeah.
See you Wednesday. Have a good one.
Sorry, say that again. Oh, or did he say bye? Okay.
You see you on Wednesday, Professor.
Sounds good.
Thank you. Bye-bye.